parametric equations and introduction. So we're going to start by listing a few of the relationships that you have come across previously defined between two variables. So, for instance, relationships as simple as y equals 3x plus 4, a linear relationship between x and y. Y equals x squared, a very simple quadratic relationship. Y equals sine x, a trigonometric relationship. And x squared plus y squared equals 9, the equation of a circle. These relationships, which are purely in terms of x and y, are referred to as Cartesian equations, named after the mathematician René Descartes. So these are in terms of the variables x and y. You may have referred to the Cartesian plane, which refers to your x and y set of axes. We're going to introduce a different kind of relationship now. We're going to introduce something called a parametric relationship. So let's start with a very simple example. X is going to equal 2t and y is going to equal t squared. So rather than defining a relationship between x and y, we define x in terms of another variable t and y in terms of this variable t as well. And this variable t is referred to as a parameter, and these are a pair of parametric equations. There is still a connection between x and y. If x depends on t and y also depends on t, then x and y must have a relationship between them too, which is something we'll explore in a little bit more detail. Now in this example, we've chosen to define x and y in terms of a parameter t. We could have used a different letter. We could have used theta or u or p, etc. But t is quite commonly used. So let's imagine t is equal to 7. Then instantly we can work out that x is equal to 14 and y is equal to 49. So x and y can still be calculated, but rather than calculating y using a relationship in terms of x, we calculate both x and y based on our value of t. So we're going to explore this example in a little bit more detail. Here are the parametric equations that we've just seen. X equals 2t, y equals t squared. And I'm going to set up a table. The first row of my table is going to be for the t values. Now I'm deliberately choosing simple integer values, which are 0 or above, but of course t could be negative, t could be non-integer, it could be fractional, decimal, etc. I'm just doing this for simplicity for the moment. So x, we can calculate x values using the fact that x equals 2t, so we can fill in the table of x values, nice and simply. And we can also calculate y, because y is equal to t squared. So remember, the calculations are based on the t values. And what we have on the set of axes below are the coordinates. Now, they've been plotted as x, y coordinates. So, for instance, here, we can see in this coordinate up here, this is the point 10, 25. But it refers to a t value of 5. Again here, this is the point 8, 16, so this point here, but it refers to a t value of 4. And we can do the same thing with all of the coordinates. So each point on the curve has an x-coordinate, a y-coordinate, and a value of the parameter t. Now, remember we said that x and y are both related to t and so relate to each other. If I take the first equation here, x equals 2t, and I rearrange it, that tells me that t could be expressed as x over 2. If I then substitute this into the second relationship, y equals t squared, so I replace t with what t is in terms of x, I get y equals x over 2 squared, which can be simplified to give me y equals x squared over 4. So I have eliminated the parameter t by substituting one equation into the other one, and that allows me to define the relationship between x and y in its Cartesian form. And of course, y equals x squared over 4 is a parabola. So this explains the curved shape of the graph. Obviously, we only allowed t to be 0 upwards, so that doesn't give us all of the quadratic curve. We only have one portion of it. Let's have a look at another example. Here are my parametric equations. And you can see both x and y have been defined in terms of t. X equals t over 2, y equals 1 over t squared. And we're going to do the same thing that we did previously. We will set up a table. I'm still going to stick with integer values for t, but I'm going to deliberately choose certain values. So here are my values of t that I have chosen specifically. Having chosen values of t, this then allows me to calculate values of x. Now, of course, that gives me a value of 0 here, half, 1 and 2. And I can calculate values of y as well. So y equals 1 over t squared. So remembering it's t that needs to be substituted into calculation. So that gives me 1 over 16, 1/4, 1. Now, 0 isn't going to give me a defined y value, so I ignore that one. 1, 1/4, and 1 over 16. Now, as you can see, there's a sketch of the graph on the axes below, and again, if we pick a particular point, for instance here, we can see its x-coordinate is a half, its y-coordinate is 1, but the graph does not display its t value. We would have to look back at the table or to use the coordinates to know that the t value here at this point is equal to 1. As we did in the previous example, we can explore the direct relationship between x and y. If I take the first equation, this one here, x equals t over 2, and rearrange this, it gives me t equals 2x. And then if I substitute that into the second result, so y equals 1 over t squared, that's 1 over 2x all squared, which is 1 over 4x squared, which is a reciprocal function and would have the shape of the curve that we can see here. So we've identified that the Cartesian relationship, or the Cartesian equation, is y equals 1 over 4x squared. So we're going to have a look at how we can convert between parametric and Cartesian equations. Here's an example to start us off with. You can see the parameter t, in which both x and y have been defined, and I'm going to call this equation 1 and equation 2 for clarity. We are going to eliminate the parameter t, which will allow us to have a Cartesian relationship between x and y. So I'm going to start with equation 2, and I'm going to rearrange this. So y equals 2t. Let's rearrange that. So t equals y over 2. And I'm going to substitute this into equation 1. So equation 1 tells me I've got x equals 2 lots of y over 2 to the power 4 plus 3 lots of y over 2 to the power 2. So I've replaced t with y over 2. And I can simplify this a little bit. So x equals y to the power 4 over 8 plus 3y squared over 4. And if we want to tidy this up a little bit further, we can multiply through by 8. So 8x equals y to the 4 plus 6y squared. And you can explore the shapes of these graphs on your graphical calculator. We'll be talking a little bit later on about how to plot parametric curves. So let's have a look at a second example. This one is a little bit harder. X equals t plus 1 over t and y equals t minus 1 over t. There isn't an obvious easy way of rearranging one of these so that t is the subject. So I'm going to do something else. I'm going to add together both equations. So equation 1, add equation 2. On the left-hand side will give me x plus y, and on the right-hand side, the plus 1 over t and the minus 1 over t will cancel, and I'll be left with 2t. So x plus y equals 2t. I can then rearrange this to tell me that t is equal to x plus y over 2. So I now know what t is in terms of x and y, and I can now choose either equation 1 or equation 2, and I'm going to replace t by x plus y over 2. I am going to substitute back into equation 1. It really won't make a difference. The end result will be the same. Substitute into equation 1. So this gives me x equals, and instead of t, I've got x plus y over 2 plus 1 over t, so that's 1 divided by x plus y over 2. I'll write it like that for the moment. So x is equal to x plus y over 2, and that's the same as plus 1 multiplied by 2 over x plus y. Rather than dividing by the fraction, we'll multiply by its reciprocal. So let's simplify this a little bit. We have x equals x plus y over 2 plus 2 over x plus y, and I'm going to multiply through all three terms by 2x plus y. So this will give me 2x x plus y is equal to x plus y all squared plus 4. So I've eliminated the denominators. I can then, and I'll make some more space up over here, simplify this carefully. So let's expand the brackets on the left-hand side. We've got 2x squared plus 2xy, and on the right-hand side we've got x squared plus 2xy plus y squared plus 4. So we get a neat cancellation here and here, and the whole thing simplifies down to give me x squared minus y squared equals 4. And again, you can explore the shape of this later on by plotting these graphs on a graphical calculator. Just as an aside, there is an alternative method that you might like to explore. If you work out what x squared is, so you square this result here, you will find you get t squared plus 2 plus 1 over t squared. Don't just copy that down, have a go at the algebra yourself. And if you square y, going back to the original parametric equations, you'll find you get t squared minus 2 plus 1 over t squared. And then you can see from here, if you work out x squared minus y squared, then the t squared terms will cancel, the 1 over t squared terms will cancel, and you're left with 2 minus minus 2, which gives you an answer of 4. So there are lots of neat ways of manipulating some of these more complex equations. Be creative with your algebra. Be accurate, but be creative. So example 3, we're actually going to have a look at converting from a Cartesian equation to a parametric format. So quite a nice simple example. The Cartesian equation is y equals 1 over 1 minus x squared, and we are given that x is equal to t. So we've got one of the parametric equations already. So very simply, y is then equal to 1 over 1 minus t squared. And underlined in green, we have our pair of parametric equations. So next example, we're given a Cartesian equation connecting x and y equals x plus 1 all squared, and we are also given that x can be expressed as e to the power of t. Substituting this in, this then gives us y equals e to the t plus 1 all squared. So converting from Cartesian to parametric can be a much simpler experience. So we're going to have a look at some parametric equations involving trigonometric functions now. So for the first example, I'm going to define the parametric equations. Here they are. X is equal to 2 cos theta. Y is equal to 3 sine theta. So because theta is the symbol that's traditionally or typically used to represent an angle, rather than defining the parametric equations in terms of t, I've defined them in terms of the parameter theta. Remember we said earlier, it doesn't have to be the letter t, that's just a typical example. So what are we going to do with these? We are going to eliminate the parameter theta and find a Cartesian relationship between x and y. So I'm going to call this equation number 1, this one equation number 2 for clarity. Equation number 1, I'm going to take this and I'm going to rearrange it so it tells me that x over 2 is equal to cos theta. Similarly, with equation 2, I'm going to rearrange this so it tells me y over 3 equals sine theta. And if I can get down to this stage here, things are going very well because I know that there is a relationship between cos squared theta and sine squared theta. So what I will also do is write down here, cos squared theta is going to equal x over 2 all squared, which is x squared over 4. And sine squared theta, which remember, this means sine theta all squared. This, of course, means cos theta all squared. So this is equal to y squared over 9. Now we know there is a trig identity that tells us that sine squared theta plus cos squared theta is equal to 1, or equivalent to 1. So this tells me that y squared over 9, which is sine squared theta, plus x squared over 4, which is cos squared theta, must be equal to 1. And here is the Cartesian relationship that links x and y. Now let's have a go at plotting the graph for this. So I'm going to choose some x values and I'm going to see what happens to the resulting y values. So let's choose x equals 0. Now if I substitute x equals 0 into this Cartesian equation, this will give me y squared over 9 equals 1. So y squared equals 9, which means y equals plus or minus 3. So that means this graph must cross the y-axis at 0, 3 and 0, negative 3. I will similarly sub in y equals 0, which this time gives me x squared over 4 equals 1, which gives me x squared equals 4, and x equals plus or minus 2, which means that there must be a pair of x-intercepts at 2, 0 and negative 2, 0. Now the shape of the curve will be like this. It is in fact an ellipse. And again, you can explore this a little bit later on using your graphical calculator. An interesting thing to take note of, For instance, if we have y equal to 0, well, let's look at the parametric equation for y. Y equals 3 sine theta. Well, this means that if y is 0, 3 sine theta is equal to 0, so sine theta must equal 0, and theta equals 0. So at this point here, we know that theta equals 0. And of course, there is another value of theta that will allow sine theta to be equal to 0, and that's theta equals 180 degrees, which is this point over here. And we can do the same thing with the parametric equation for x, and we will discover that theta equals 90 degrees here. Theta equals 270 degrees. And this links in with a topic that those of you who study further maths will be working on later on, which is the concept of something called polar coordinates, where coordinates are defined partly in terms of an angle. So let's look at a slightly more complex trigonometric example. My parametric equations are up here. One of these is in terms of sine theta, and the other contains sine 2 theta. Now, this second one should immediately ring some alarm bells for you, because of course you know there is an identity for sine 2 theta. Y equals 2 sine theta cos theta. There's the identity. Now, that still doesn't help us completely, because the first parametric equation, the one for x, does not give us a substitution for cos theta. It only allows us to substitute in for sine theta. Let's rearrange it anyway. So sine theta is equal to x plus 1. But remember the identity that connects sine theta and cos theta. We know sine squared theta plus cos squared theta is equivalent to 1. Sine squared theta we can now replace with x plus 1 all squared. So x plus 1 all squared plus cos squared theta equals 1. Cos squared theta equals 1 subtract x plus 1 all squared, and cos theta equals the square root of 1 subtract x plus 1 all squared. Because there's a square root involved here, we need to ensure that the contents underneath the square root are positive, so this will only really be valid for a limited set of x values. We can now substitute cos theta back into the equation for y, so this gives us y equals 2, and instead of sine theta I'm going to write x plus 1, and instead of cos theta I'm going to write the square root of 1 minus x plus 1 all squared. So let's move on to have a look at the parametric equation of a circle, or the parametric form of the equation of a circle. So our circle is going to have a centre to start off with at the origin, 0, 0, and it's going to have a radius of r. Now we know the Cartesian equation for a circle with these dimensions would be x squared plus y squared equals r squared. Let's pick a point on the circle. I'm going to pick a point over here, just for simplicity. It could be anywhere on the circumference of the circle, but I'm going to make the visuals of this a little bit easier. Now the point P is going to have coordinates x and y, and I'm going to draw in the radius connecting to P to the origin there. I'm now going to draw in a right angle triangle from P down to the x-axis and along like that, and I'm going to label this angle here theta. Now of course, along here we have x, along here we have y, and what I'm now going to do is identify x and y in terms of r and this angle theta. So let's think about the sine of theta. This would equal the opposite, y divided by the hypotenuse r, and I can then rearrange that. Y equals r sine theta. So theta could be my parameter, r would be a known value of the radius. I then have one of the parametric equations. Similarly, cos theta, that's the adjacent x divided by the hypotenuse r, and this then can be rearranged to give me x equals r cos theta. So I have my parametric equations here. And again, assuming r is some known numerical value, the parameter I'm basing this on is theta. So let's now have a look at a circle which is not centred on the origin, a circle that has a centre AB but still has a radius r. Let's draw that radius in and let's label a point P which has got coordinates x and y. We can still draw in our right angle triangle like this, and we can still label an angle theta, but we have to be a little bit more careful because remember, x is measured from here through to this point here, and y is the whole of this distance across here. So I'm going to refer to the base of the right angle triangle here, and I'm going to refer to the height of the right angle triangle here. So sine theta is going to equal the height of my right angle triangle divided by r, which will rearrange to give me the height of my right angle triangle equals r sine theta. We'll use that in a moment. Cos theta is going to equal the base, or the adjacent, divided by the hypotenuse r, which rearranges to tell me that the base of my right angle triangle is equal to r cos theta. But of course, I now need to identify x and y. So x is, of course, this whole yellow distance here, which is the measurement a plus the base. So x is equal to a plus the base, which means x is equal to a plus r cos theta, and this is one of my parametric equations. And again, similarly, we can see y is this distance here, which is b, plus the height of the right angle triangle, which is this, which gives us the whole value of y. So y is equal to b plus the height of the right angle triangle, which means y is equal to b plus r sine theta. And here, highlighted, we have our parametric equations. So to end with, we're just going to outline a few techniques that you can use with your graphical calculator to sketch parametric curves. Make sure you practice this carefully so it's clear to you how to plot graphs using parametric equations on the calculator. The first thing that you need to do is to make sure that you are in graph mode. And then when the option for inputting different equations comes up, you need to access F3, which changes the type of graph that you are drawing. F3 again allows you to draw a parametric curve. You'll see that the button says something like param. Now, that then gives you a set of options that looks like this. So your screen will say xt1, yt1, and then there'll be options for xt2, yt2, etc. Now, of course, if you're inputting more than one pair of parametric equations, you then need more than one pair of slots. But if you're just inputting a single set, you only need the first and second slots here. So have a go at inputting some of these sets of equations that we have looked at parametrically. You may also need to adjust the window settings to make sure that you have an appropriate set of axes. So make sure you remind yourself how to do that. So you can access the axes by pressing Shift, which then brings up a new menu. And then you want F3, which says View Window. Now, when you press View Window, it will look like there's only the option for inputting X and Y scales, but if you press the downwards arrow and keep going, you will find you get to something that says T theta and an option for min and max, and this will allow you to set the values of the parameter. So for instance, if you want your parameter, which we'll call t, to be between -3 and 5, you would set the t min to be -3 and the t max to be 5. There is then another option called pitch, or PTCH, and that gives you the level of accuracy of the calculations involving t. If you want the calculator to calculate a t coordinate and a corresponding x and y coordinate at every 0.1, you can set that. That will give you a more accurate and a more smooth and continuous graph than if you set t to be a larger value, for example, t equals 1. Then fewer coordinates will be calculated. Have a go and see if you can plot some parametric curves.